answers to the questions I assigned yesterday. Does anyone have any comments, questions, concerns, anything you'd like me to demonstrate? Okay. Malik and Lexi says no one has questions. Malik changed his mind. Find the kinetic energy of a car which has a mass of 1,000 kilograms moving at a rate of 20 meters per second. Okay. Okay, so it says find the kinetic energy, EK. So let's use the formula. EK equals 1/2 mv squared. Write down the mass, 1,000 kilograms. Write down the velocity, 20 meters per second. Plug everything in. Half times 1,000 times 20 squared. 20 squared is 400. 400 divided by 2 is 200. 200 times 1,000, 200,000. There you go, Malik. Boom. No, because it's exactly the same. They're all exactly the same. EK equals 1/2 mv squared. The mass is 0.8. The velocity is 10. So you have 1/2 times 0.8 times 10. So you're squared. So you're going to have 0.4 times 100, which is going to be 40. Where'd you go wrong, Soham?
For 0.8 times 1/2, I got 1.6.
So you sort of doubled it, but even then not really, because you said 1.6? So you doubled it, you didn't divide it by 2. Okay. Okay, so we did a bunch of math already, so I would like to not review bed mass again a second time. How do we feel about skipping a lesson on bed mass so you guys have more time to work on the real stuff? Okay, I'll show you the bed mass you need to know in the questions that we're going to assign. Skip ahead, jump to here. It's going to look a lot like what we did yesterday, but yesterday you only found kinetic energy. What if instead I gave you the kinetic energy and asked you to find me the mass? Or I gave you the kinetic energy and I asked you to find the velocity? What if, what if that? And so that's today's lesson and some other stuff. So here we go. A bunch of examples. Same formula. We're starting the same way. Kinetic energy is 1/2 mv squared. It's important to recognize, though, that you can write 1/2, the fraction, as 0.5, the decimal. Same thing. Important to recognize this. By grade 10, that should be something you're comfortable with. And do not, please, just rush ahead and do all these questions, because I'm going to change some of the details about some of the questions as we go. So do not just bust ahead and solve everything, because I'm going to make it more interesting. Here we go. Number 1. Number 1 is going to go exactly the way you expect it to go. Some of you have already done number 1. How much kinetic energy does a 5-kilogram bowling ball moving at 10 meters per second have? It does have 250 joules. How'd you do it? Well, if the question says how much kinetic energy, that's the formula we're using. 1/2 mv squared. We know the mass is 5, the velocity is 10. We can plug and chug our way to victory. So 1/2 times 5 times 10 squared, and that's relatively easy to solve because 10 squared is 100, times 5 is 500, half of 500 is 250, and so we have 250 joules. That's yesterday's work. Here's today. Let's make it more interesting. Instead of wording a question the way question number 2 is worded, let's make some tweaks here. Question number 2 is going to say, it says, find the velocity of a 5-kilogram bowling ball that's traveling at 250 joules of kinetic energy. Here's how it will be worded instead. We're going to make the ball lighter. We're going to say, okay, instead of a 5-kilogram ball, we're going to make it a 3.6-kilogram ball. For reasons. And instead of saying that it's traveling with 250 joules of kinetic energy, what we're going to say is that it is traveling with the same kinetic energy as the 5 kg ball was. And this is how you're going to be presented with these kinds of questions. You'll be like, okay, Find me the kinetic energy of the 5 kilogram bowling ball that's moving at 10 meters per second. You did that. It's easy. Congratulations. Now, question 2 will say, here's a lighter object. How fast will the lighter object be or how fast will the lighter object be moving if you give it the same amount of kinetic energy? So it's that extra little step. It's like, okay, I need to take the answer I had from the previous question and pull it down. Now we're giving the ball the same amount of kinetic energy, 250 joules, but it's a lighter ball. The mass now is 3.6 instead of 5. For those of you who have ever been 10-pin bowling, this 5 kilogram ball is a 12-pound ball. This 3.6 kilogram ball is an 8-pound ball. You grabbed a ball that is lighter off the rack, and now you're going to throw it instead. Do you expect it, if you throw it the same hardness, do you expect it to go faster or slower? A lighter ball, you've given it the same energy you gave the heavier ball. You'd expect it to go faster. So let us see if your intuition is correct. It's the same equation, but we're given different values. We're going to use EK equals 1/2 mv squared. But now we're given that the mass is 3.6 and the kinetic energy is 250. So the kinetic energy is going to go over here, where EK was in the formula. So 250 goes on the left-hand side. That's going to equal 1/2 times 3.6 times v squared. And now we can go ahead and solve for v. What's the first thing we need to do? Yeah, we can multiply the 3.6 and a half. Yeah, oh no, we're not going to know. The exponent's not first because the exponent's on the variable. That's the last thing that we're going to deal with. A way to make your life a lot easier is to do this piece first. What's half of 3.6? 1.8. So we're going to get 250 is going to equal 1.8 v squared. What's the next step? We are not going to minus both sides. You got the right idea. How are the 1.8 and the v squared attached? They're being multiplied. So what's the opposite of multiplying? Lemmy said division. You betcha. So we're going to divide by 1.8 on both sides. That's going to cancel those two. And we're going to get that 250 divided by 1.8 is 138.9. And that's going to equal v squared. So now we need to get v alone. We need to square root both sides. Boom, boom. And v is going to equal, what is the square root of 138.9? Hey, Capri, coolest animal you've ever seen. In person. Up close. An elephant. Nice. Were you writing the numeracy test? No. Okay. How fast is the bowling ball going? 11 point. So let's round it to 11.8. But 11.7, is it 11.7? It's 11.78 something. Okay, so 11.79 or 11.8 meters per second. You need the units in there. I don't care if you give it to me to 1 decimal place or 2. And so your intuition was correct. You took a lighter ball, you threw it the same hardness, and faster. Let's do another one. A car is traveling at 10 meters per second. We're going to tweak that. A car is going to be moving at 5 meters per second. Nice and slow. Sorry, and we're not changing the joules. We're just changing the mass of the car. Sorry, the velocity of the car. 5 meters per second, just so we're clear. 5 times 3.6 is 18. So you're in like a parkade somewhere, 18 kilometers per hour. Maybe you're in a parking lot. And if this car traveling at 5 meters per second has 25,000 joules of energy, how heavy is the car? Well, let's take a look. You are given a velocity, you're given an energy. So it's important to recognize that a moving object is going to use this equation. This is important to recognize because today and tomorrow I'm going to give you 2 more energy equations. And you're going to have to figure out which is the best one to use. So for a moving object, it's always kinetic energy. EK equals half mv squared. The mass, we don't know. The velocity is 5. The kinetic energy is 25,000. So now we're going to plug these values in and find M. 25,000 is going to equal 1/2 times M times 5 squared. Yes. Technically, at this stage, that wouldn't change anything. It's possible in the future that it would. So be careful with that. Don't do it just to get lazy. What's the mass of the car? So 5 squared is 25. Half of 25 is 12.5. So we could go like 25,000 is going to equal 12.5 M. So divide by 12.5, divide by 12.5, and you're going to get a mass of what? What's 25,000 divided by 12.5? Is it 2,000? You're saying this with some hesitation. Should I punch this into my calculator? It is 2,000. So just to put that into perspective, a 2,000 kilogram car, an example of this would be like an Escalade, or the Volkswagen Touareg, or the Audi Q7, or the Toyota Highlander. These are the kinds of vehicles that we're talking about in the 2,000 kilogram range. So one of those vehicles moving very slowly, even moving slowly, has a large value of kinetic energy. Okay. I would like you guys to do question number 4. I am not changing anything on question number 4. Yes. Okay, how fast is the elevator moving? For what? 4 meters per second. I'm going to nail you for it, yeah. Got to include units. Okay. So question 4, the answer is 4. Would anybody like me to demonstrate? Yes? Okay, let's do it. Kinetic energy, if you're looking for velocity, that's an EK kind of question. We're told that EK is 4,000. We are told that the mass is 500. So we're going to get 4,000 equals 1/2 times 500 v squared. So I'm going to simplify this, Gemina. Half of 500 is 250. So we're going to get 4,000 equals 250 v squared. then to get V alone, the first thing we've got to do, we have to get rid of the thing that's being multiplied before we get rid of the squared. So we're divide by 250, divide by 250. So you're going to get V squared equals, and now 4,000 divided by 250 is 16. Square root, V equals 4 meters per second. No worries. Okay. So I want you to flip forward one page. I'm flipping backwards a bunch of pages, just for fun. We said way back when that when we were finding, or when we were going to figure out, Soham and Namrit, how much gravitational potential energy an object possessed, that the things that mattered, Malik and Angel, was the mass of the object, the height at which the object was going to be, and the gravity at the location that the object was going to fall from. So let's look at gravitational potential energy. That's where you guys, that's the page you guys are on. There we go. Here is the formula for gravitational potential energy. We're just going to take those three concepts and multiply them together. I am going to add a letter out front to represent the fact that this is a potential energy. PEG equals mg triangle H. This triangle just means change in. And more often than not, it's going to be the change from 0. So we don't actually need to write it this way. Instead, we can write it like this. We can say that the potential energy gravitational is going to equal mgh, where h is some height above a reference point. You can pick your reference point to be whatever you want it to be. Usually that reference point we call 0. Mass is still mass. G is the acceleration due to gravity. I gave you a value yesterday to make the numbers a little bit easier. We're going to round that value. Yesterday I told you that G was 9.81 meters per second squared. To make your life a little bit easier, we're going to round that to 9.8. Just one less thing to punch into your calculator. Okay, I will separate this group of 6 if you guys can't stop talking under me. Thank you. So 9.8 meters per second squared is the value that we're going to use for G on Earth. If somehow I give you a question on the moon, that value is going to change to 1.6. Yes, Malik? Sorry? You bet. Mass, again, always given in kilograms. Let's go for it. There is a bell at the top of a tower 50 meters high. That 50 meters, just to put that into perspective, is with 17 stories. Yes, Angel, I saw that hand. You bet. This 17-story or 50-meter high bell weighs 10 kilograms. What is the potential energy of the bell? Or another way to think about it is, how much is this going to suck if that bell falls on you? Presumably not. It's not going to be a great experience. Let's see how bad it's going to be. So we are wanting to know what the potential energy is. And in this case, we only have one kind of potential energy. It's gravitational. So we're going to use that formula, PEG equals mgh, and we're going to set it up the exact same way we set things up before. M is 10 kilograms. H, oh, I didn't say it before. H always needs to be given in meters. Always in meters. So this question gives it to us in meters. That's great, but if it gave it to you in kilometers or centimeters, you'd have to convert. Height always needs to be in meters. In this case, we have that. Height's going to be 50 meters. And you know G on Earth is 9.8. So let's plug it in. And this is nice and easy. It's a plug and solve. Potential energy, gravitational, is going to equal the mass, 10 times G, 9.8 times the height, 50. And you're going to find that the potential energy of this object is what? 4,900 joules. This is not an overly difficult calculation to do. You take your values, plug them in, and away you're going to go. Okay. I will do either question 2 or 3. It's the exact same calculation. Which one would you like me to do? Sure, we can do question number 3, which means you guys are going to do question 2 and question 4 here in a second. Here's question 3. A roller coaster is at the top of a 70-meter hill. It weighs 100 kilograms. What is the potential energy of the roller coaster? That is a very light roller coaster. 100 kilograms, 220 pounds. I am the roller coaster. Just to put that into perspective. Me the roller coaster, very small roller coaster. Well, how much potential energy do I have as the roller coaster? 70 meters up the hill. 70 meters is pretty far. That's 3/4 of a football field straight up. It's impressive. How much potential energy do I have? If I were to fall on you from 70 meters, how much would that suck for you? And me, but mostly you. So, we've got the mass. Mass is 100 kilograms. The height, 70 meters. G is 9.8. You take those values and we're going to plug them into the equation. Potential energy gravitational is equal to mgh. So, mass is 100, G is 9.8, H is 70. We're going to multiply those values together, and what do you get? How much gravitational potential energy do I have 70 meters above the ground? 68,600. It's going to suck a whole lot more if I fall on you from 70 meters versus that silly little bell we had in the previous question. Because that's a whole lot more energy that I will be transferring to you. Okay, I want you to do questions 2 and 4. On your mark, go. You bet. Okay. How much gravitational potential energy does the 10 kilogram mass have 2 meters above the ground? Malik is correct. Question number 2, what's the answer? What'd you get? 196.2 joules. And question number 4, how much potential energy? None. If the object is on the ground, it cannot fall to the ground because it's on the ground. No potential energy for an object that's no height above the ground. Cool. Let's make this more interesting, shall we? Oh, sorry, 196. My bad. I used a different value for G with my previous class. We used 9.81, not 9.8, and I just made things more decimal. We changed it. Okay, flip the page. If you recall, we discussed once upon a time the law of conservation of energy. Law of conservation of energy says that energy is neither created nor is it destroyed. It's transformed or transferred between forms or from one object to another. So what that means is that the total energy at the beginning needs to equal the total energy at the end always. So we've got the energy initial. Mathematically, what this means is that the initial energy has to equal the final energy. Regardless of what energies you have, all of them at the beginning need to be equal to all of them at the end. Don't freak out, computer. You're okay. Keep doing what you're doing. So, at this stage, let's say I gave you this problem. We've got a roller coaster. The roller coaster is moving at 5 meters per second, and the roller coaster is 70 meters above the ground. What kind of energies does that roller coaster have at this point? It's moving at 5 meters per second, 70 meters above the ground. What kind of energy does the roller coaster have? Sorry? You're answering my question, Dennis? No? Okay. Roller coaster is moving at 5 meters per second, 70 meters above the ground. What do those two pieces of information tell you? There's gravitational. What part of what I said tells you there's gravitational, Soham? Because it's up. It's 70 meters up. But it's also moving at 5 meters per second. So if it's moving at 5 meters per second while it's up there, what kind of energy does it have? Answer my question and you can go to the bathroom. Answer my question and you can leave. Okay, so here's my question. If you have a roller coaster moving at 5 meters per second, 70 meters above the ground, what kind of energy does it have? Soham already said gravitational because it's 70 meters above the ground. If it's also moving at 5 meters per second, what kind of energy does it have? Kinetic. Have a great day. See you later. So at the beginning, this roller coaster has kinetic energy initial and it has potential energy gravitational initial. It has both of those forms of energy. Put your phone away, Malik. Oh, you're not on your phone? Okay, it looked like you were hiding your phone. Okay. So if they've got kinetic energy and potential energy at the beginning, it is reasonable that I could concoct a scenario where there's kinetic energy at the end, EK final, plus PE gravitational final. You now have to take into account all these pieces. In an ideal, and we're going to show you how this gets done. In an ideal situation, 100% of the energy of one form would get turned into another form. Is that reasonable? If I take an object and I let it fall, will all of its potential energy turn into gravitational in the real world? No. Why not? Friction of the air is going to heat up the object. There will be energy lost to the generation of heat. For the sake of these questions, because that's mathematically difficult to do, we are going to ignore that portion of the problem. This is not realistic. Because of air. And so to solve that problem, we are going to ignore air. Because that's easy, right? We will ignore air. So here's a problem for you. We are at a height, or you are at a height of 10 meters above the ground. That's 3.5 stories. So you are like another half a classroom above this one. We're on the 3rd floor. You stand on the roof, you'll be at 10 meters. You have a ball. The ball weighs 2 kilograms. And gravity is 9.8 meters per second squared because you're on Earth. The ultimate question that we're going to ask, or we're going to answer here is, how fast is the ball going to be moving when it impacts the ground? And here's how we go about that. We're going to break this thing up into a couple steps. It's important to recognize, physics is mathy, But believe it or not, the language of physics is wildly important. The language that we use implies a bunch of information. We are going to drop this ball. What does it mean for us to drop the ball? What are the implications of that choice? It will fall. Will it have any velocity to start if we're dropping it? No. What word would I have used instead if it was going to have some velocity at the beginning? We'd throw it. We're not doing that. We're dropping it. So dropping it means, what kinds of energy does this ball have at the beginning of the problem? It has potential energy. Does it have any kinetic energy? If it's not moving at the beginning of the problem, does it have any kinetic energy? No. So the kinetic energy is going to be 0 here. And we don't know yet what the potential energy is. We're going to calculate it in a second. But we can say that the ball is not going to be higher than it is right now. So this is going to be some maximum value. The potential energy does not get any larger than it is right there. The ball will fall. It's going to impact the ground. At the moment of impact, what kind of energies does that ball have? The second it impacts, or the instant it impacts the ground, it will have kinetic. Kinetic is not 0 until the ground stops the ball. Before the ground stops the ball is moving. It's going to suck for whoever is responsible to catch the ball at the bottom. And at this stage, the instant it impacts the ground, the kinetic energy is going to be a maximum here, and the potential energy is going to be 0. At the moment of impact, there is no potential energy. The ball is in contact with the ground. And the kinetic energy is a maximum. So all of the potential energy has been converted into kinetic energy. So let's go ahead and work out the problem. Now, when you do a problem like this in Physics 11, like my class is going to do this today. My Physics 11s this afternoon are going to do this problem. They will not have it broken up the way you have it broken up here. I'm going to give them the problem, and I'm going to say find the final velocity, and I will bring in air resistance to what they're doing this afternoon. You guys don't get that. And you guys get this, the hand holding here is what this is. These questions are going to be broken up for you into 3 steps. First, what is the potential energy of the ball? We know it's going to be a maximum value because the ball is at its highest height. So what is it? Well, potential energy gravitational is given to us by mgh. We know the mass of the ball, 2 kilograms. We know the height of the ball, 10. We know the gravity of the ball, 9.8. We know the gravity of Earth is 9.8, sorry. So we're going to take those 3 values, we're going to multiply them together. We've done that math already once today. 2 times 9.8 times 10 is going to be 196 joules. Now, we have already said that the potential energy here is a maximum and the kinetic energy is 0. We've said that the potential energy is 0 at the bottom, and so the kinetic energy has to be a maximum. We also said, if we slide back up here, that energy is not being lost. All of one form of energy has to turn into the other form of energy. There was no kinetic to start, there's no gravitational at the end. So, without doing any more math, how much kinetic energy does the ball have the instant it turns, or the instant it hits the ground? It's got to be the same as the potential energy it started with, 196. So the kinetic energy here is going to be 196 joules, all of the starting potential. That's a P, not a V. All of the initial PE turns into KE because we're assuming 100% efficiency. And for most of what you guys would do in life, that would be true. I mean, there's extreme scenarios. You up to the top of the Empire State Building, you start hucking stuff off. That's going to be, you're going to have to deal with air resistance. You go skydiving, you have to deal with air resistance. You don't accelerate all the way to the ground when you skydive. There's a maximum velocity a human being will reach. It's about 220 kilometers per hour. because air resistance becomes a thing when you're skydiving, thankfully. But for this kind of scenario, we can ignore air resistance without much of an impact. So we found the potential energy. We recognize that all the potential energy is going to get converted to kinetic. So then, how fast must the ball be moving on impact? Well, if we're looking for the velocity, the formula we're going to use is the formula for kinetic energy. EK is going to equal 1/2 mv squared. We know that EK is going to be 196. We know the mass of the ball is 2. So we can go ahead and we can plug this thing in and we can find out how fast the ball is going to be moving. 196 is going to equal 1/2 times 2 v squared. This is a really beautiful set of numbers here because what's half of 2? 1. And then 1 times v squared is just going to be v squared. So I'm going to have 196 is equal to v squared. And what is awesome about 196? 196 is a perfect square. If you had me for Math 9, I had you memorize all the perfect squares up to 400. So the square root of 196 is 14. 14 meters per second is equal to v. To put that into perspective, you'll understand 14 meters per second is about 50 kilometers per hour. That ball is moving as fast as cars travel at speed limit on your average city street when it impacts the ground or whatever's underneath it. Cool. Comments, questions, concerns about what I've done here? If there are no questions, I'd like you to flip the page and I'd like you to write down these numbers. Here are the numbers you're going to write down. 1.02. 220,500. 450. 4.47. 6. 76.7. 205,800. 55,125. They're all on the screen. 4. 45.9 and 49.5. Those are the answers in no particular order to the questions I have assigned on the upcoming pages. If it helps while you're doing these questions, draw a picture so that you can visualize what's happening here. In fact, that's what you're going to have to do for question 5A. Flip the page. For 5A, I want you to draw. That is how you answer 5A. Draw the picture. But I'll leave the answers up here on the screen for those of you who haven't written them yet. This is the rest of class. I want you to play with these concepts. Let me know how I can help you. Good luck. May the force be with you.